Good morning, one and all. So, today we start our class. Now, in the last class, I have explained about TDM, which means time division multiplexing. So, where we transmit multiple number of signals over a channel at different times or by dividing in time. Okay, how it is possible? So, it is possible like this. So, we transmit one after another. Obviously, we receive one after another. So, here we have something called commutator, and we also have decommutator, which is opposite of commutator. So this is the TDM diagram. So here we are transmitting multiple number of signals, n number of signals by multiplexing in time. So here, as I told you with example, what we do here is, suppose we are transmitting 3 signals. So our commutator will collect samples of those 3 signals. Okay, so here our commutator will rotate in the anti-clockwise direction. So it will rotate in the clockwise direction. Okay, now so commutator is a sampling device which takes n samples in one cycle. Okay, it takes each sample from each signal over a period of ts seconds. Otherwise, commutator takes ts seconds to complete one rotation. So to complete one rotation, it takes ts seconds. Okay, and so in the process of this rotation, it will collect one sample from each one of these signal. Okay, same thing happened here. So these are the samples of these 3 signals. Our commutator is collecting. This is over a period of ts seconds. Here what is doing? It is collecting one sample from each of these 3 signals. So that is over one rotation. The next rotation, it will collect these 3 samples. Okay. So like this. So when it completes one rotation, it will collect a sample from each of these n signals. Here we are transmitting how many signals? 3 signals. Here capital N equal to 3. Okay. Now, so like this it will collect. So this is nothing but reconstruction. The sampling, it is something like reconstruction. Okay. In between we have a modulation and demodulation. Now, so the number of message signals is equal to capital N. So we want to multiplex capital N number of signals, and number of bits per sample is small n. Okay. So we will quantize the samples. How we quantize? By using an encoder having a small n number of bits. So each and every sample will be quantized by using small n number of bits. Okay. Now, so this is the small n is the number of bits per sample. Now what the bit rate would be? So it is n into capital N into small n by ts. Otherwise n into small n by fs. Okay. So what do you mean by this? So if you observe this example. So let me take this example. In ts seconds, we are transmitting 3 samples. Correct? 3. Why 3? Because here capital N equal to 3. Isn't it? Now, so here in ts seconds, so we are transmitting 3 samples. Correct? Now, as I told you just now, each and every sample will be encoded by using how many number of bits? Small n number of bits. Which means in ts seconds, we are transmitting. In ts seconds, we are transmitting 3 into n number of bits. Why? We have 3 samples and each sample is represented by n number of bits, small n number of bits. So in total, we are transmitting 3n bits in ts seconds. Okay. What is the bit rate? Number of bits per second. Okay. So here, if you go by logic, simple logic, so in ts seconds, we are transmitting 3 into n number of bits. So in 1 second, how many will you transmit? Obviously 3n by ts. Correct? Isn't it? So in 1 second we transmit 3n by ts. Otherwise 3n by fs. ts is nothing but the sampling period, the overall sampling period. So here what is 3 actually? 3 equal to capital N. Okay. Now that is the logic here. So bit rate is nothing but n into small n into capital N by fs, or small n into capital N by ts. So this is about an example we have taken already, we have discussed yesterday also. Now here I have given some problems, you try to find out. So here 10 message signals are TDM, I mean time digit multiplexed. Each is band limited to 5 kHz using 8-bit TDM, which means we are representing each and every sample using 8 bits. So the sampling rate is twice the Nyquist rate, find the bit rate. So just now I explained the formula, try to find out the answer. I gave in the answer also, you try to find out. So the one more example also I given, so you try to solve these two problems. Okay, so the logic is, this is the logic. So with that logic, try to find out the answer for those two questions. Okay. Now, so we have started this signal space analysis. I told you already, it is very important. It is purely mathematical. So it is very important to understand the digital modulation techniques. So pay your attention. So if you don't understand this signal space analysis, it is very difficult to understand the digital modulation techniques. So anyway, this is the typical digital modulation diagram. So where we represent everything geometrically. So this is I explained in the last class also. So this is very important. So we have to represent everything geometrically. Whether we represent the transmitted signals as well as noise, received signal, everything will be represented geometrically in a space, signal space. Okay. Now, so as I told you in the last class, the transmitter is emitting or it is producing SI of t. Okay, where I varies from 1 to m. So energy signals, m energy signals. So we want to represent that energy signal as a linear combination of n orthonormal basis functions. Okay, so this is what the linear combination. Okay, now so SI of t is, if you expand this summation, it would be SI1 phi 1 of t plus SI2 phi 2 of t, so on SIN phi n of t, where I varies from 1 to m, j varies from 1 to n. Please remember this. Capital M will be always greater than or equal to small n. So what is capital M and what is capital N? M is, so the number of signals that we are transmitting. Here, so this transmitter is producing S1 of t, S2 of t, so on Sm of t. Now what is capital N? They are the number of basis functions. So we will see how to generate those basis functions. Okay. Always the number of transmitted signals will be more than or equal to the number of basis functions that we use to represent them as a linear combinations. Okay. Now, so this is Sij. They are something like coefficients of expansion. They differ like this. So it is very simple to remember. Sij equal to integration 0 to t Si of t phi j of t dt. So here I have written very clearly, I varies from 1 to m, j varies from 1 to n. So what is Si1? Sit phi 1 of t dt. So like this you have to find out. So I told you all those basis functions are orthonormal. Orthonormal in the sense they need to be orthogonal and they should have a unit energy. So if you take any set of signals which are orthogonal to each other, at the same time they are having unit energy, then they are said to be orthonormal set of signals. So the extra condition is they should have a unit energy. So if any set of signals which are orthogonal to each other at the same time they are having unit energy, then they are called as orthonormal signals. Okay. Now here, so this is the condition for orthonormality. Okay. Why? Because if I equal to j, which means, so we are taking same basis function. So in that case, so phi integration 0 to t phi I of t whole square dt, that is nothing but energy of phi I of t, that should be equal to 1. If I is not equal to j, which means we are finding the product of two different basis functions, so obviously that has to be 0 for orthogonality. Correct? So this is very important statement I am making here. This is very important. So what I have written here is, so the very important statement is this one. So all the basis functions are orthogonal to each other in the interval 0 to t. At the same time, they should have a unit energy. Each and every basis function should have a unit energy, and all the set of basis functions should be orthogonal to each other. Then they are called orthonormal set of basis functions. Okay. Now, so the set of coefficients are naturally viewed as an n-dimensional vector. Okay. Now here, so these coefficients Sij or can be written, they will be written in the form of a vector or a column matrix. Are we right? So Si, okay, it's a vector, it's a column matrix, Si1, Si2, so on, Sin. What is the order of this matrix? N cross 1, where I varies from 1 to m. So which means I am writing all these coefficient of expansion in the form of a vector. Okay. So here, so Si is called signal vector. So here we write everything in the form of a vector or a column matrix, something like that. Okay. Now if I equal to 1, what happens? I equal to 1 means S11, S12, so on, S1n, n cross 1. This is the signal vector S1. Okay. So what do you mean by that actually? So actually, so we have Si of t, correct? How we are writing that Si of t? Like this, correct? So Si of t is equal to summation j equal to 1 to n Sij phi j of t. Now these Sij's are written in the form of a vector, or so they are just like coordinates. Okay, I will take an example. So their coordinates, these are axes. Phi j are axes, phi j of t is an axis. These are the coordinates of the axis. Okay, I will take an example. So you just remember this signal vector. Okay. So see, we are writing everything from this diagram only. We want to represent everything that is there in the diagram in the geometrical form. Okay. Next. So now, so this is synthesizer. So here, so now this is Si. How to get Si of t? How to get Si of t? How to realize Si of t? So we have to multiply Si1 with phi1 of t. Okay, this is a product. Next, Si2 phi2 of t. Next, so on, Sin phi n of t, and add them all. Now how to get this diagram? So here I am representing this equation in the form of a diagram, nothing more than that. I am representing this expression in the form of a diagram or in the form of a figure. Otherwise, you can see simply here. How to get Si of t? Si1 phi 1 of t plus Si2 phi 2 of t, so on, Sin phi n of t. So same thing is being written here. Si1 phi 1 of t multiplication plus Si2 phi 2 of t plus so on, Sin phi n of t. If you add all those things, you will get Si of t. So it is called synthesizer. Okay. So you might have heard these things in the Fourier transform also. So there are two equations, or Fourier series or Fourier transform. Fourier series, synthesizer, analyzer. Okay, same thing. So to get Si of t, we use this diagram. So to get reverse, here what is input? Si1, Si2, Sin. What is output? Si of t. Reverse, here what is input? Si of t. What is output? Si1, Si2, Sin. It is something like, something like modulation, something like demodulation. Okay. Anyway, so you must remember these diagrams very, very carefully. How to get Si1 from Si of t? Okay, let me go back. How to get Si1 from Si of t? You take this equation very, very carefully. So how to get this equation? How to get Si1 from Si of t? What do? You take Si of t, multiply with phi 1 of t, and integrate this product over 0 to t, you get Si1. How to get Si2? You get Si of t, multiply with phi 2 of t, and then integrate the product over 0 to t. How to get Si3? So on, so on. Okay. So same thing is written here. Okay. So what is the common here? See. So for Si1, Si2, Si3, what is the common? Si of t is common. What we are changing? Phi 1 of t, phi 2 of t, phi 3 of t, so on, so on. Here same thing I am writing. Si of t common input. Now if I multiply Si of t with phi 1 of t and integrate over 0 to t, what do you get? Si1. Here what is Si1? You can tell me. So integration 0 to t, Si of t, phi 1 of t dt. Same thing. correct? So how to get SI2? So integration 0 to t, SI of t, phi 2 of t dt, so on so on. This is how we get SIN. So this is very very important. So this, for this equation we have one figure, for this equation we have another figure. So it is a synthesizer, it is an analyzer. Okay, just like Fourier series or Fourier transform, we have Fourier transform, inverse Fourier transform. In the same way, it might be a modulation, it might be a demodulation. Okay, why? Because so it is something like modulation, because this is a message signal multiplied with carrier. Okay, again, so it is a modulated signal, it is again multiplied with the same carrier with some extra terms, extra operations. Okay, so I will explain everything in detail later, but you just remember these two diagrams, they are very very important. So the entire digital modulation techniques are based on these two diagrams only. So please pay your attention to these two diagrams. Okay, now so here in these two diagrams, what is unknown? Unknown things are these basis functions. We don't know what are they. See this this SI12, everything is depends upon phi 1 of t, phi 2 of t only. You look at these equations first of all. So in this equation, what is important thing? Phi j of t. Here also what is important thing? Phi 1 of t, phi 2 of t, phi 3 of t, so on so on. So here to implement these two equations, we need to know what are those basis functions. Correct? Okay. So here it is very very essential to find out the basis functions. So if at all you want to construct these two diagrams, you must know. So because these are very very important. In this diagram also we have these basis functions. Here also we have common things are, what are they? These basis functions. How the basis function should be? They should be orthonormal, which means they should be orthogonal as well as they should have unit energy over 0 to t. So please remember, so if I say any statement, it is only applicable to, or I am making statements which are restricted to 0 to t only. I am not talking what happens beyond t. Please remember this. All our statements, all our analysis will be restricted to 0 to capital T only. Okay. Why? Because so this is a discrete or digital communication where so at each and every t seconds we get a new symbol. Okay, so the next symbol would be independent of the previous symbol. Okay, so they are highly independent. So we don't bother what happens after capital T seconds, because so let me go back to the basic diagram. So here the source is emitting some symbols at each and every capital T seconds. So we only bother about capital T seconds. What is the behavior of this channel, this transmitter, this receiver from 0 to t only? Because after t seconds we get another symbol, okay, which might be different from the previous symbol. So that's why all our analysis will be restricted to 0 to t only. Okay. Now, so this is what as I told you just now. So we can represent everything geometrically. So let me take simple example. Signal space, we call it as a n-dimensional Euclidean space, or also called as signal space. Okay. So in the signal space, what happens? How to represent all the digital modulation in a signal space or in a geometrical space? Here I am taking a simple example. 2-dimensional signal space with 3 signals, which means so m equal to 3. What is m? The number of transmitted signals. We have 3 energy signals and we have 2 basis functions. Obviously, as I told you, m must be greater than or equal to capital N. Here I have taken m is more than n. You can take equality also. Okay. So capital M is always will be greater than or equal to small n. Okay. I have taken it for example only. It is only for example purpose. Now, so I varies from 1 to m, which means 1 to 3. J varies from 1 to n, capital N, which means 1 to 2. So n equal to 2 means 2 basis functions phi 1, phi 2 as axis. Here, so here basis functions will act as an axis. Why? As I told you, the basis functions are orthonormal, which means they are orthogonal as well as they have unit energy. That's why we represent axis with a basis functions, not xyz. In this signal space representation, we use basis functions as axis. Okay. Now, so 3 signal vectors. Okay, why 3 signal vectors? Because as I told you just now, SI. Okay, I varies from 1 to m, which means 1 to 3. What is S1? Here m equal to 3, n equal to 2. Now, what is S1? S11, S12. Correct? S11, S12. What is the size of this vector? 2 cross 1. That's it, 2 cross 1. What is S2? S21, S22. What is S3? S31, S32. These are 3 signal vectors. Okay, so please pay your attention to these signal vectors. Correct? Okay. Now, so how to write the signals? How to write S1 of t? Here I am going to this basic equation. What is S1 of t? Here n equal to 2. I varies from 1 to 3 because m equal to 3. 0 to capital T. This should be written everywhere. Now what is S1 of t? Summation j equal to 1 to 2 Sij phi j of t. You expand this. What do you get? You get like this. S1 of t equal to summation j equal to 1 to 2 Sij phi j of t. That is S11 phi 1 of t plus S12 phi 2 of t. What is S2 of t? S21 phi 1 of t plus S22 phi 2 of t. What is S3 of t? S31 phi 1 of t plus S32 phi 2 of t. Now here I have written these 3 energy signals as a linear combination of phi 1 of t, phi 2 of t with the coefficients of expansions as S11, S12, S21, S22, S31, S32. So this is the basic thing. Okay, so everything I am using this basic equation to write these 3 equations. You just pay your attention. You take a pen and paper, try to write everything step by step. Okay, you will understand very clearly. Now, so this is simply representation of these 3 signals as a linear combination of 2 basis functions phi 1 of t, phi 2 of t, which are obviously has to be orthonormal. Okay, here, so we don't know what are phi 1 of t, phi 2 of t. We don't know still. Okay, we have to find out them. But what is the corresponding signal vector? S1. This is S1 signal vector. S2, S3. Okay, you go to the basic equations, you will find out. You can find out. Now, so by defining so, I can able to represent them in a signal space of what dimension? 2 dimensional. So dimension depends upon capital N. What is capital N? N number of, that is number of basis functions, which is always less than or equal to capital M, the number of transmitted signals. Here, so since I have taken 2 basis functions, now they are as axis, phi 1 axis, phi 2 axis. Here we don't write t, we neglect t. So why? Because here the basis functions are phi 1 of t, phi 2 of t, no? So we don't write in terms of t, we just write phi 1, phi 2. Because here we are dealing the distance, not time. Okay, so that's why we omit the variable t. It vanishes, only phi 1, phi 2. Okay. Now, so just like x axis, y axis. Okay. So this is a S1 signal vector. This point represents, let me write clear, this point represents a signal S1. This point in a geometry represents signal S2. This point represents a geometrically signal S3. Okay, so this is a line joining the origin to the signal message point. We call it as a message point. Okay, this is origin. Correct. Now, what are the coordinates of this point? What are they? What are the coordinates of this point? Generally, S11, S12. What about this? S21, S22. What about this? S31, S32. Okay. So here these are the points in a signal space, in a 2-dimensional signal space. This is this point coordinates are S11, S12, S21, S22, S31, S32. So what are those points? These are the coordinates, obviously, isn't it? So here, can you tell me what is the length? This is a vector, no? Signal vector actually. What is the length of this vector S1, or what is the length of this point, this line? This is the origin. This is here. It is the origin. Here it is S11, S12. Correct. What is the length of this line? Square root of S11 whole square plus S12 whole square. What is the length of this line? Square root of S21 whole square plus S22 whole square. What is the length of this line? Square root of S31 whole square plus S32 whole square. You know how to find length from the origin. Correct. So origin, this origin, these are the, this is 0, 0, this is S11, S12. You find out the length of the line. Okay. Now, so we have something called norm of a vector. It is denoted like this: norm or length or norm by this symbol. Okay. Now, just now I told you, so the square of the length of a signal vector SI is, what is that? So square of length equal to this much. Okay. So in this example, what is the square of a length of this line? S11 whole square plus S12 whole square. What is the square of length of this line? S21 whole square plus S22 whole square. What is the square of length of this line? S31 whole square plus S32 whole square. Okay. So here I have written in this form. So it is also equal to SIT transposition into SI. What is SI? It is signal vector. Okay. Now, so that is same as energy of the signal. So what is energy of the signal? EI. What is energy of SI of t? That is EI, that equal to integration 0 to t SIT of t whole square dt. I varies from 1 to m. Okay. So here this important statement is energy of the signal is same as square of the length of the vector. Which means, so if you can able to find out the square of this length, that will be exactly equal to energy of the signal SI of t, S1 of t. In the same way, so if you can able to find out the square of the length of this line, that gives you the energy of the corresponding signal. Same thing here. Okay. So to find out energy, just find out the square of the length. Geometrically, we represent all the signals in a signal space. You just find out the square of the length, you can find, that means that is equal to energy. Okay. That is very, very important. Okay, so in the above example, so what is norm S1 square? That is S1 transposition into S1, that equal to, what is that? S11 whole square plus S12 whole square. In the same way, what is the square of the length of the signal vector S2? That is norm S2 square equal to S21 whole square plus S22 whole square. Same thing here. But the square of the length also equal to energy of the signal E1, E2, E3. Okay. So this is also very, very, very important. So this is how we find out the coefficients. So for your understanding, I have written some examples. How to find S11? Integration 0 to t, S1 of t, phi 1 of t. S12, S1 of t, phi 2 of t, dt, integration. Same thing. S22, S21. S2 of t, phi 1 of t. You just remember this logic. S31, S3 of t, phi 1 of t dt. S32, S3 of t, phi 2 of t dt. You just remember these logics. Okay. Now, so here, so till now we have seen the length of the vector or the square of the length of the vector, or the length is also called as norm. Okay. Now in the same way, so how to find the distance between two vectors like this? I want to find out what is the distance between these two vectors, or these two vectors, or these two vectors, or these two lines. Okay. So how to find out? This formula. Generally, you know how to find out the distance between 2 points in a diagram, I mean the geometrical diagram. So this is what we find out. So this is the square of the distance between two signal vectors Si, Sk. That is norm Si, Sk whole square equal to this much. That is also equal to this much. Simply. So integration 0 to t Si of t Sk of t whole square dt. Okay. Now, so this is called the distance between two signal vectors Si and Sk, or square of the distance between these two vectors will be this much. You try to find out this. In the same way, can you tell me, so what is the distance between S1 and S2? What is that? What is the square of the distance between signal vectors S1 and S2? It would be simply S11 minus S21 whole square plus S12 minus S22 whole square. Okay, in the same way, you find out the square of the distance between S1, S3, S2, S3, S1, S2, like that. Okay. Now, not only that, so there is something called angle between two signal vectors, which means I want to find out what is the angle between these two signal vectors. So I want to find out, so these are two signal vectors. Just want to find out this signal vector, what is the angle between them? Otherwise, so what angle between these two signal vectors? Something like that. So you know already, signal vectors means, angle means, suppose we have two vectors A and B. How to find angle between those two vectors? A dot B by mod A into mod B. Something like you might have studied. Same thing here. So, but we take transposition. Okay. So, cos of theta ik equal to SIT transpose into SK by norm SI into norm SK. Okay. So, it is also just like simple mathematics only. It is nothing that difficult. Okay. So, these are all things we have discussed about signals in a geometry. Okay. So, here finally I want to conclude by saying this. So, here we can represent all the things in a n-dimensional signal space. So, we can also find out the distance between any two signal vectors. We can find out the norm length of any signal vector. We can find out the angle between any two signal vectors. Here we can represent signals with a point in a signal space. Just this point represents a signal. If you take one more point, this point represents another signal. Okay. So here, so that's why it will be very, very easy to analyze. Why? Because so we are representing signal with a point. So if it is a point, we can find out the length of that point. We can find out energy. We can find out the distance between 2 points. We can find out the angle between two signal vectors or 2 points, etc., etc. Okay. Now, so analysis will be very, very easy if you can able to write everything geometrically. Okay. Now, so these are some simple things about the geometry. Now, so there is a procedure called Gram-Schmidt orthogonalization procedure. Okay. So this is very, very important procedure. Okay. Why? Because till now, so in the previous discussion, everywhere we need to know two things. I mean, very important thing. What are they? These basis functions. How to find those basis functions? We have to find out those basis functions. Okay. And they should be orthonormal, which means all the basis functions should be orthogonal or perpendicular to each other. At the same time, each and every basis function should have a unit energy. Okay. At the same time, the number of basis functions would be always less than equal to the number of signals that we are transmitting. Okay. Or capital M. And one more thing. So the dimension of this signal space depends upon the number of basis functions. Suppose if there are 3 basis functions, it would become 3-dimensional signal space. If it is if there are n basis functions, this would become n-dimensional signal space. Okay. So that's why we have to choose or we have to find out those basis functions. For that, there is an algorithm or procedure that is called Gram-Schmidt orthogonalization procedure. Okay. It has got 4 to 5 steps, very, very simple steps. So let me go briefly. First of all, so we have to take the set of m energy signals that we wish to transmit. Okay, so if you go back to diagram, as I told you in the last class itself, so here we have a source which is emitting symbols at each and every t seconds, and those will be transmitted, modulated, and we are transmitting Si of t, which means, so we are transmitting S1 of t, S2 of t, so on and so on, Sm of t. So those are m energy signals. Okay, first we should take those things. Okay, first of all I have taken those set of m energy signals. Why they are energy signals? Why they has to be energy signals? Because each and every signal is defined only from 0 to t, which means otherwise each and every signal is defined only over a duration of capital T seconds. Okay, S1 of t, S2 of t, all are defined only over a duration of capital T seconds. So if any signal is which is time bounded, there has to be energy signals. Okay, now so these are the set of energy signals we have. Step 1, starting with S1 of t, choose an arbitrarily from the set. You take any one signal from the set. We have a set of m energy signals here. You take any one signal. First of all, I am taking S1 of t. How to get phi 1 of t? S1 of t by square root of E1. What is E1? Energy of S1 of t. Correct? S1 of t by root E1. Why I am doing like this? Can you tell me the reason? The reason is, if I do like this, the energy of phi 1 of t will be equal to 1. You find out energy of phi 1 of t? It is 1. You might have seen these kind of things in S and SS. Okay. Anyway, so what is S1 of t from this equation? It is root E1 into phi 1 of t. Root E1 into phi 1 of t. Okay. But, so what is root E1? That is S11. Why? So let me go back to this equation. So here S1 of t equal to, take only this part. Correct? S1 of t equal to S11 phi 1 of t. Correct? Here what I have? Here S1 of t equal to root T phi 1 of t. So S1 of t equal to S11 phi 1 of t. But so we compare these two. S11 has to be equal to root E1. And phi 1 of t will have a unit energy as required. This is the first step. What do we do? So from the set of m energy signals, take one signal, divide that signal with a square root of its energy. You get a first basis function. You find out energy of phi 1 of t. What will happen? Integration 0 to t phi 1 of t whole square dt. That is what energy of phi 1 of t, isn't it? Do you agree with me or not? What is phi 1 of t whole square? S1 of t whole square by E1. You're right. S1 of t whole square by E1. What is integration 0 to t S1 of t whole square? That is nothing but energy of S1 of t. But what is E1? Energy of S1 of t, which means energy of S1 of t by E1. Both are same. Both will cancel out each other. Obviously get 1. So the energy of phi 1 of t will be equal to 1. You tried yourself. Okay. That is the first thing we do. So we have found out one basis function. So please remember, we have to find out how many basis functions. Capital N number of basis function. What is the capital N? Always less than or equal to capital M. How to decide? Okay, we will see. This is a procedure. Okay, the first step. This is step 1. What is step 1? So from the given set of m energy signals, take one signal, divide that signal with the root of its energy. So that gives you the first basis function. So here it has got unit energy as required. What is required actually? Our basis functions has to be orthonormal, which means they should be orthogonal and they should have a unit energy. Since I have only one basis function as of now, so there is no point of there is no question of finding the orthogonality, because when I talk about orthogonality, we should have minimum of two functions, isn't it? So that's why as of now I don't talk about orthogonality, because I have found out only one basis functions. I can only check for unit energy, which I am done just now. Are you getting or not? Okay. Next. So next is using S2 of t. Next. So these things you should know. S1 of t, S2 of t, S3 of t, so on, so on, Sm of t should be known to you. Okay. Take S2 of t. So what do you know? From the step 1, you know phi 1 of t. From the given set of m energy signals, you know S2 of t. If you know these two, S2 of t, that is from the set of m energy signals, phi 1 of t is from the first step. If you know these two, you can find out S21. Okay, that is second step. You have to find out S21. Okay, so in the third step, we have to introduce an intermediate function g2 of t. Okay, so pay your attention here. G2 of t should be introduced. What is G2 of t? That equal to S2 of t minus S21 phi 1 of t. Okay. Now, so we have to find out an intermediate function G2 of t, that is S2 of t minus S21 phi 1 of t. Now here we know S2 of t, that will be given to you. S21 we have found out in the second step. Phi 1 of t we have found in the first step. In the third step, we have to find out first of all the intermediate function G2 of t. Okay. Next. So after finding this, you have to find out energy of G2 of t. How to find energy of G2 of t? 0 to t G2 of t whole square dt. But what is G2 of t? S2 of t minus S21 whole square, S21 phi 1 of t whole square. Substitute here. That equal to expand this. Expand this. What happens? S2 of t whole square plus S21 whole square phi 1 of t whole square minus 2 into S2 of t minus into S21 into phi 1 of t whole square, phi 1 of t dt. I am just expanding this square term. Okay. So you do separate integration. Integration 0 to t S2 of t whole square dt. What is this? E2, energy of S2 of t. Eg2 is energy of G2 of t. E2 is energy of S2 of t. Please find the difference. Now S21 is a constant. Why? Because it is a coefficient. Take outside. S21 whole square. What is 0 to t phi 1 of t whole square dt? What do you mean by that? It is energy of phi 1 of t. Obviously, it should be how much? 1. So this will be 1. Minus 2 into S21 minus 2 into S21 S2 of t phi 1 of t dt. What is this? What is integration 0 to t S2 of t phi 1 of t? What is that? S21. So please pay your attention here. Already have S21 here. I am just asking this integration. It is also S21. So that's why this is E2. Correct? This is 1. That's why S21 whole square minus 2 S21 into S21. 2 S21 whole square. So E2 minus S21 whole square. Okay. So simply energy of G2 of t, that is Eg2 equal to E2 minus S21 whole square. Simply you can find out. Okay. Now, so how to find out next basis function? So to find out second basis function, phi 2 of t equal to G2 of t by square root of its energy. What is G2 of t? It is called intermediate function, which is defined as, how it is defined? S2 of t minus S21 phi 1 of t. So G2 of T by, what is energy of G2 of T? That is Eg2, just now we found out. How much? E2 minus S21 whole square, substitute here. Clear? Now, so what is the energy of phi2 of T? It will be always obviously 1. Why? Because G2 of T by square root of its energy. Obviously find out this energy of this signal, it would be 1. Okay. Now, so this is you get phi2 of T. So phi1 of T, phi2 of T. Yeah, now we have to check two things. Since we got two basis functions, we should check orthogonality as well as unit energy. So just now I verified phi1 of T, phi2 of T are having unit energies. But this phi2 of T should be perpendicular to phi1 of T. Okay, you can check whether these two are orthogonal or not. You try to find out this. You try to find out this integration. You get 0 or not. Okay, you try yourself. Integration 0 to T, phi1 of T, phi2 of T dt. Okay, they should be orthogonal. So phi1 of T, anyway, leave it. What is phi2 of T actually? Phi2 of T equal to G2 of T by some energy. What is G2 of T? S2 of T minus S21 phi1 of T. Substitute here. Try to get the answer. It will be 0. Okay. I am not doing here. You try to find out. So this is the fourth step. In the fourth step, we have found out two basis functions. Now, next step. One more intermediate function. G3 of T. What is G3 of T? S3 of T minus S31 phi1 of T minus S32 phi2 of T. Now from the previous steps, we found out phi1 of T, phi2 of T. S3 of T will be given to you. So we have to find out phi3 of T. How to get phi3 of T? Just same procedure. It repeats. Okay, you follow the same procedure. How to get phi3 of T? G3 of T by its energy. G3 of T by root of Eg3. Okay, you proceed like this. So how to get S31? I told you somewhere here. S31 is integration 0 to T, S3 of T, phi1 of T. You know S3, you know phi1. How to get S32? Integration 0 to T, S3 of T, phi2 of T. You know those things. These two things also given to you. You know already. Just find out S31, S32. So after finding S31, S32, you find out G3 of T by root of its energy. You find out, you get phi3 of T. You continue in this fashion. Okay. So generally, now just how to define next intermediate function, G4 of T. How to define? So here, what is G2 of T we have defined? S21 minus, S2 of T minus S21 phi1 of T. Correct? G3, S3 of T minus S31 phi1 of T minus S32 phi2 of T. G4, how to define G4? S4 of T minus S41 phi1 of T minus S42 phi2 of T minus S43 phi t of 3. Okay, so on so on. So this is how we define. So Gk of T equal to Sk of T minus summation j equal to 1 to k minus 1 Skj phi j of T, k equal to 1 to n. Okay, you just try to find out what is G4 of T. S4 of T, okay, S4 of T minus j equal to 1 to k minus 1 Skj phi j of T. Correct? Okay. So this is the standard intermediate function. G1, G2, G3, G4, G5, G6, so on, so on. How to find out the basis function? After finding the intermediate function, divide that function by root of its energy. So j varies from 1 to n. So these are the generalized forms of intermediate function and the basis function. Okay. Now here, so one thing is not clear till now. How to decide the value of capital N? I told you already, N always should be less than or equal to capital M, or capital M should always be more than or equal to capital N. Okay. So here it depends upon these two factors. These are very, very important. So the signals S1 of t, S2 of t, so on and Sm of t are from a linearly independent set, in which case n equal to m. Okay. So if the given set of signals, if the given set of m energy signals are linearly independent of each other, then m equal to n. Okay. If they are not linearly independent, what do we do? In which case m will be more than n. So the intermediate function gk of t equal to 0 for k greater than n. So we will take a simple example. We will try to find out. Okay. So just observe these 4 signals. Here I have given these 4 energy signals. Correct? So by giving these 4 set of energy signals, I am asking you to find out the basis functions. Now, so here I did not tell you how many basis functions are required. Obviously, they are less than or equal to 4, because here what is capital M equal to? The number of energy signals, 4. I have given these 4 signals. So obviously the number of basis functions are less than or equal to 4. You have to find out they are equal to 4 or less than 4, or simply I have to find out what are the exact number of basis functions that we need. Okay. Now, so here I made a statement here. It depends upon linear independent nature of the set of given m energy signals. What do you mean by that? Here S1 of t, S2 of t, S3 of t, S4 of t is given. Okay. Now how to get S4 of t? If I add S1 of t, it is 0 to t by 3. If I add S1 of t plus S3 of t, what I get? Just add S1 of t plus S3 of t. What will happen? Simple addition of 2 signals. What will happen? You get S4 of t. Isn't it? S4 of t is the addition of S1 of t plus S3 of t. Correct? Now, next. So here they are not set of linearly independent signals. Okay, here okay, S4 of t is linear combination of S1 of t, S3 of t. So which means, so S4 of t is a linearly dependent, not independent. So that's why only these 3 are linearly independent. Why? Because you cannot write S1 of t in terms of S2 of t and S3 of t. Okay. So here, so linearity means you should not take any time scaling, all those things. Only you can do amplitude scaling or addition and amplitude scaling. Okay. So you may think like that. So if I do time expansion, something like that, S2 of t equal to S1 of 2t, something like that. No. So linear independent sense means, so S2 of t should be written in the form of S1 of t linearly. Maybe you can write 2 into S1 of t or 3 into S1 of t, something like that. Okay. So S1 of t is independent of S2 of t and S3 of t. Okay. So only these 3 are a set of linearly independent signals, not 4. S4 of t clearly depends upon S1 of t, S3 of t. Okay. Now in this case, so since even though there are given signals are 4, but among 4 signals, one is dependent on these 2 signals. That's why we have only 3 set of signals which are linearly independent. Here, so from the given set of 4 signals, we are forming a subset of linearly independent signals. Now the subset contains only 3 signals. Isn't it? So that's why capital N equal to 3. So here, so they are not linearly independent. That's why m will be greater than n. So m equal to 4, n equal to 3. Suppose if they were independent, if they were linearly independent, what would happen? Here n equal to 4, m equal to 4, both would be same. Okay. So how to decide the number of basis functions? It is simply the set of energy signals which are linearly independent of each other. Okay. So if all the given set of m signals are linearly independent, obviously m equal to n. If not, so we form a subset which contains only a set of independent signals. So those number of signals will be equal to capital N, that equal to number of basis functions. Okay. So now we form a subset having only these three signals. You try to solve this thing. So try to find out step by step. So S1 of t I am writing in this form. It's a mathematical form. So since S4 of t equal to S1 of t plus S3 of t, so it is linearly depend upon these two. This is the reason. So only 3 are forming a set of linear independent signals. That's why n equal to 3. M equal to 4. So here m is more than n. Why? Because one signal is depending upon the previous other signals. So if all the given signals were linearly independent, m would have been equal to n. Okay. Now you try to solve this. Okay. We stop here. We try to solve this. That is homework.